man is called Richard Clayderman. He is a famous German popular pianist who combined classic music and modernist music perfectly with his talent. This scene is similar with the first time that I saw his concert in my appreciation. He sat seriously that by the Steinway piano, which was one of the most famous brand of pianos in the world. From his hands, I could hear the spring flowing past, I could see the flowers blooming. At that time, feeling excitement about piano pushed me extremely eager to rush to
Now that we know just a little bit more about waves, we are now able to apply mathematics to music. For this example, we are going to be using two sets of two notes. The first set will consist of the note C and the note G, which sounds nice together, obviously. It's rather consonant. And then the second set of notes would be C and F sharp, which is just a little bit more dissonant, or doesn't sound as well together. Not that it sounds bad, but it has obviously a different tonality to it. Why would that be?
The reason that the notes of the C major triad sound consonant to each other instead of dissonant is actually quite simple. When we look at the frequencies of the three notes and write them as proportions to each other, the notes come out as almost rational. The proportion of C to E is about 5/4, the proportion of C to G is about 2/3, the proportion of E to G is about 5/4 as well.
So the topic of waves brings up an interesting sort of concept, and that is the concept of being out of tune. What makes being out of tune sound so bad? Well, it's actually quite simple when you look at it this way. So let's draw the wavelength for, I don't know, the note A. This is not a scale drawing, I should mention. So if that's our unit here right there. If we draw our wavelength of A, looks just like that. And as you can see, it goes up and down and up and down. It's probably standard A right there. Now, the frequency of A is A440, just like that. So what if we had a wavelength, or frequency rather, of A441? What would happen then? Well, what would happen is that because the frequency is just that much shorter, this is once again not scale drawing, it would probably start to do this, and then as you can see, the wavelengths begin to be completely different. Now, if this is A441 and this is A440, what happens is eventually A441, which is out of tune with A440, is going to be at a completely opposite point in its wavelength than A440 is. And this will cancel out the sound for just like a split second. It's very, very subtle, but it is noticeable, and it does produce a very ugly tone.
Now I keep on mentioning frequencies in terms of numbers, and you're probably wondering how I obtained these numbers. Well, there is in fact a formula in order to find out the frequency of a note. It's rather simple, but it looks intimidating. The formula is Hz equals 6.875 times 2 to the 3 plus MIDI pitch power divided by 12. The MIDI pitch is simply a standard used in music to determine the value of a note. For example, the MIDI value for C is 60, so the equation would look like so. Every single note in a scale can be calculated in a similar way, as long as you know the correct MIDI value for the note. Obviously, there are numerous other areas of music and math that I could have explained as well, but they are rather trivial and do not have as much relevance as the various concepts that I have described. Mathematics explain numerous earthly functions, and clearly music is no exception.